Hello student, welcome to my lecture, paper number 13, Functional Analysis 2, Unit 3, the structure of the commutative Banach algebra. Let X be a topological space, script C of X is equal to the set F such that F from X to C continuous and bounded function. Theorem, let A be a commutative Banach algebra and let M be a maximal ideal of A, then Banach algebra A quotient M is a division algebra and it equals the Banach algebra C of complex number, and the natural homomorphism x2 x plus m of A onto A quotient M is equal to C. Assign to each elements of a complex number xm defined by x of m is equal to x plus m, and the mapping x to x plus m has the following properties. First, x plus y of m is equal to x of m plus y of m. Second, alpha x of m is equal to alpha into x of m. X into y of m is equal to x of m into y of m. Fourth, x of m is equal to 0 if and only if x belongs to m, and 1 of m is equal to 1 no mod x of m is less than or equal to norm x. Proof. Here A is commutative Banach algebra and M is maximal ideal of A. Now we have the following result. If I be a proper closed two-sided ideal of A, then A quotient I is a Banach algebra. Here M is maximal ideal, so M is closed. Hence by the result A quotient M is a Banach algebra, because I is proper closed two-sided ideal of A, then A by I is a Banach algebra. Here M is maximal ideal and closed, so A by M is Banach algebra. And also we have the result, if M is maximal left ideal in A, then A by M is division algebra. So A by M is Banach algebra, and so A by M is a division algebra, and also we know that if A is division algebra, if A is division algebra, then A is equal to C. Here division algebra A by M. So A by M is equal to C, hence it equals the Banach algebra C of complex number. Now we take a natural homomorphism phi, and phi defined A to A by M defined as phi of x is equal to x plus m is equal to x of m. X plus y of m is equal to x plus y plus m by this, and x plus y plus m is equal to x plus m plus y plus m. This is equal to x of m, and this is equal to y of m. Second, alpha into x of m is equal to alpha x plus m is equal to alpha into x plus m is equal to alpha into x of m. Xy of m is equal to xy plus m is equal to x plus m into y plus m is equal to x plus m is equal to x of m, y plus m is equal to y plus m. Fourth, x of m equal to 0 if and only if x plus m is equal to m, if and only if x belongs to m. 1 of m is equal to 1 plus m. This is identity in a quotient m, and this is equal to 1. Mod x of m is equal to norm x plus m is equal to infimum of norm x plus m, such that x belongs to m, and this is less than or equal to norm x. Now the Gelfand mapping x of m is equal to x plus m, and a tends to a by m is equal to c. Here x is fixed and m is maximal ideal of a, which is variable. If script m is the set of all maximal ideals of a, then x of m is a complex function defined on script m. This function we denoted by x cap x cap. So x cap defined script m to c, and x cap of m is equal to x of m is equal to lambda, and x of m is equal to x plus m tends to lambda into 1 plus m. Let a cap is equal to the set x cap such that x belongs to a. We defined a topology on script m as the weakest topology generated by a cap. That means it is the weakest topology on script m relative to which every function x cap is continuous. Now, any sub-basis open set has the form sub-basis name capital S of x cap m0 epsilon equal to the set m belongs to script m such that mod x cap of m minus x cap of m0, this is less than epsilon. We call the topological space script m to be the maximal ideal on maximal ideal space. The mapping x to x cap of A onto A cap is called the Gelfand mapping. It is clear that x cap belongs to script C of script M. So a cap subset of script C of script M, and also a cap is equal to 1 because a cap of M is equal to 1 of M, and is equal to 1 plus M is equal to 1. Now the next theorem. The Gelfand mapping x to x cap is a norm decreasing homomorphism of A into script C of script M with the following properties. Here given we have to prove these four properties first property is the image A cap of A is a subalgebra of script C of script M, which is separates which separates the points of script M and contain the identity of script C of script M. And second, the radial R of A equals the set of all elements X for which X cap is equal to 0. So X to X cap is an isomorphism if and only if A is semi-simple. And a definition of semi-simple are equal to 0. Third property, an element X in A is regular if and only if it does not belong to any maximal ideal if and only if X cap of M not equal to 0 for every M belongs to script M. And last, if X belongs to A, then sigma of X is equal to X cap of script M. The range of X cap and R of X is equal to supremum of the set mod X cap of M such that M belongs to script M is equal to norm X cap. Now we see the proof of the theorem. Let function phi defined from A to script C of M defined as phi of X is equal to X cap and X belongs to A, and X cap from script M to script C, X cap of M equal to lambda, where X of M is equal to lambda into 1 plus M. First, we prove phi of X plus Y is equal to phi of X plus phi of Y. Here X of M is equal to lambda into 1 plus M, this, and Y of M is equal to mu of 1 plus M. X cap of M is equal to lambda and Y cap of M is equal to mu. Now X plus Y of M is equal to X of M plus Y of M. Put the value X of M. X of M is equal to lambda into 1 plus M plus value of Y of M is equal to mu into 1 plus M. Now simplifying this, 1 plus M is common, so we get lambda plus mu into 1 plus M. So X plus Y cap of M is equal to lambda plus mu because this X cap of M is equal to lambda. Here X plus Y of M is equal to this. So the value of X plus Y cap is equal to lambda plus mu. So this value, and lambda is equal to X cap of M plus mu is equal to Y cap of M. This value, this, and lambda is equal to this, mu is equal to Y cap. So this value, and so X plus Y cap is equal to X cap plus Y cap. So phi of X plus Y is equal to phi of X plus phi of Y. Now to show phi of alpha x is equal to alpha into phi of x. So we take alpha x into m is equal to alpha x of m. X of m is equal to x plus m. So alpha into x plus m, and x plus m is equal to lambda into 1 plus m. Now alpha x cap of m is equal to alpha into lambda, and the value lambda is equal to x cap of m. So alpha into x cap of m, so this is equal to alpha x cap is equal to alpha into x cap. So phi of alpha x is equal to alpha into phi of x. Now third, phi of xy is equal to phi of x into phi of y. Now let x into y of m is equal to x of m into y of m. X of m is equal to lambda into 1 plus m, and y of m is equal to mu into 1 plus m. Now 1 plus, and now the next step is equal to lambda into mu into 1 plus m. Now x plus y cap of m is equal to lambda into mu by the definition, and lambda is equal to x cap of m into mu is equal to y cap of m. So this is equal to x cap into y cap of m. So x into y cap is equal to x cap into y cap. So phi of xy is equal to phi of x into phi of y. So phi is homomorphism from a into script c of script m. So phi of a is equal to a cap is a subalgebra of script c of script m. So mod x cap of m is equal to mod x of m. This is less than or equal to norm x. So x to x cap is a norm decreasing, and therefore it is continuous. Now we prove of first property. We want to show that m1 is not equal to m2 implies x cap of m1 is not equal to x cap of m2. So we let m1 is not equal to m2. There exists x belongs to a. There exists x belongs to a such that x belongs to m1 and x does not belongs to m2 because m1 is not equal to m2. Now x belongs to m1, so x plus m1 is equal to 0, and x plus m2, x does not belongs to m2, so x plus m2 not equal to 0 because x of m is equal to 0 if and only if x belongs to m. This implies x of m1 equal to 0 and x of m2 not equal to 0. So this is equal to x cap of m1 is equal to 0, and this is equal to x cap of m2 is not equal to 0. So this is equal to 0 and this is not equal to 0. So both are not equal. So x cap of m1 is not equal to x cap of m2. 1 of m is equal to 1 plus m, and 1 into 1 of 1 plus m. So 1 cap is the identity. This is complete the proof of property 1. Now proof of second property. Since R is equal to intersection of M maximal ideal set of all maximal ideal, so x belongs to R if and only if x belongs to M for every m belongs to script m. if and only if x plus m is equal to m. If and only if x of m is equal to 0, x of m is equal to x cap of m equal to 0 for every m belongs to m. If and only if x cap is equal to 0, so R is equal to set x belongs to A such that x cap is equal to 0. So phi of x is equal to x cap, and phi is the isomorphism. If and only if phi is equal to x cap and phi is an isomorphism, if and only if kernel is equal to 0, if and only if x belongs to A such that phi of x is equal to 0 is equal to 0 and phi of x is equal to 0, so phi of x is equal to x cap is equal to 0 because of phi of x is equal to x cap, and this is equal to, this is if and only if r is equal to 0 because r is equal to x belongs to A such that x cap is equal to 0, and this is definition of semi-simple. So this is if and only if A is semi-simple. This is complete the proof of property 2. Now the next property 3. X is regular implies x does not belongs to M for every M belongs to script M, because M is a proper subset of A. If x belongs to A, this is x is regular implies M is equal to A, which is not possible, implies x plus M, x plus M, x does not belongs to M, so x plus M is not equal to M, so x cap of M is not equal to 0. Now converse, suppose x cap of M is not equal to 0 for some M belongs to script M. If possible, suppose x is singular, we have to prove x is regular. So we suppose contradiction and the proof this is not true. So x is regular. Consider the set ax is equal to yx such that y belongs to A. Then Ax is a proper ideal of A containing X. So Zone's lemma, by Zone's lemma, there is a maximal ideal M such that X belongs to Ax subset of M. So if this implies X belongs to M, X belongs to M implies X of M is equal to 0. We know that x of m is equal to x cap of m equal to 0, which is contradiction to x cap of m is not equal to 0, hence x is regular. Thus x is regular if and only if x does not belongs to m for every m belongs to script m. Here the third property complete the proof. Now proof of fourth. Sigma of x is equal to x cap of script m, and r of x is equal to x cap norm x cap. Now lambda belongs to lambda belongs to sigma of x now lambda belongs to sigma of x if and only if x minus lambda into 1 belongs to s, if and only if x minus lambda into 1 cap of m is equal to 0 for some n belongs to m, if and only if x cap minus lambda into 1 cap of m is equal to 0, So x cap of m minus lambda into 1 cap of m is equal to 0. This is equal to lambda is equal to 0. So x cap of m is equal to lambda. So sigma of x is equal to x cap of script m. Now r of x is equal to supremum of the set mod lambda such that lambda belongs to sigma of x, and this is equal to x cap of m. So this is equal to norm x cap. So r of x is equal to norm x cap. Thank you.